Presented by Caltech.
Good evening. Thank you all for coming out tonight. It's my pleasure to introduce my colleague, Heather Knutson, who has been with us at Caltech for a number of years now. She just recently got tenure this spring. She was a graduate of Johns Hopkins University in 2004, where she majored in physics. She then went on to Harvard to study with Dave Charbonneau, where she graduated in 2009, and then she went to Berkeley as a Miller postdoctoral fellow, and then in 2011 she came down to Caltech. She had a really prominent role in the Spitzer mission, even as a graduate student, where she was the principal investigator of a major experiment that gave her thousands of hours of time observing that telescope. And she was really part of the first wave of people discovering, astronomers discovering exoplanetary systems that she'll talk about tonight. She's part of a group that Fiona and Harrison and I are really proud of, a very fertile collaboration between the Division of Geological and Planetary Sciences and Physics, Math, and Astronomy. And she interacts regularly with people like Dimitri Maui and Andrew Howard, Konstantin Batygin, and Caltech is enjoying what is really a rather remarkable experience in understanding exoplanet systems. So without further ado, I'm going to turn it over to Heather, who's going to tell us tonight about the architecture of our solar system and how it compares to others. So, Heather.
All right, so it's a pleasure to be here tonight. Hopefully all of you guys are relaxed, settled after having made it through the parking lot. So tonight I want to tell you a little bit about some of the amazing planetary systems that we're finding around other stars. So this is a very new field. In fact, it's new enough that I remember the start of it. The first planets around nearby stars were found just 20 years ago. And in that time, we've racked up an amazing count. So we're now up to more than 5,000 planets and planet candidates around nearby stars. So we've gone from having no planets just being swimming in planets. But what we're trying to do right now is trying to make sense of that sort of big heaping pile of planets. So we're good at finding them, but we don't yet understand what we're finding. So the story that I want to tell you tonight is a story of some of the different kinds of planets that we've discovered. Planetary systems with very different arrangements than our own solar system, very different kinds of planets. And what I'd like to sort of bring you along is sort of the process of trying to make sense of them. Why do we end up with one kind of planetary system and not another? And this all circles back to maybe the biggest question of all, which is, are there other planets out there that might host life? So perhaps they're Earth-like, perhaps not. And if so, might we eventually discover them around nearby stars? So to frame my story, I need to tell you a little bit about how we actually search for planets around nearby stars, because it's not necessarily very obvious. Certainly, hundreds of years ago, people proposed that there might be planets around these stars, so that's not a new idea. But what really changed was it was only very recently that we came up with some clever tricks for actually detecting the presence of those planets around stars. So here's an image of the night sky taken with a small telescope. Most of the points of light in this image are stars. So the question is, there's the night sky, there's all your stars. How do you go about looking for planets around those stars? So the very simplest thing that I think comes to mind first is you want to take a picture of one of these stars, sort of really zoom in, and take a really sharp picture so that you could actually see the little faint planet kind of hiding next to the star. So you might want to take a picture that looks something like this. In theory, that's great. In practice, it turns out that's a really hard thing to do. In fact, it's so hard that this picture that I'm showing you tonight is actually cheating. So this picture is a picture of two stars. It's actually not a star and a planet. So imagine that little faint dot on the side, make it much, much fainter, and move it in much, much closer to the big, bright star. And that is kind of beginning to approach the difficulty of actually taking pictures of planets where you can see the planet next to the star. So great idea in theory, really hard in practice. We've made it work. There are a few planetary systems that have been discovered this way, but the vast majority of the planets we know about today, we're not ever actually, we don't have any pictures of them. So we're going to X that out for now. And just to kind of give you a little bit better idea of just how hard it is to take a picture of a planet next to the star, we can come up with an analogy, which is imagine getting one of those really bright, hot spotlights that you see in Hollywood. So get one of those spotlights, set it up in Hollywood, and then get a little tiny firefly and put it up next to the spotlight, maybe about a foot away. Now imagine that you, the photographer, want to take a picture where you can see that little dim firefly next to that glaring bright spotlight. But there's a catch. The spotlight and the firefly are here in Los Angeles, and you, the photographer, are located in New York City. That's about how hard it is to take pictures of planets around stars. So the fact that it's people have made it work at all is actually an amazing testimony to the power of technology. But that's actually not the story that I'm going to tell you tonight. So the story I'm going to tell you tonight focuses on a very clever workaround for this problem. So instead of trying to solve the really hard problem, sometimes it's useful to flip things around and come up with a different approach. And so what we ended up doing for exoplanets was looking for indirect evidence of the planet. So instead of trying to see the planet directly, we want to study the star, and from the properties of the star, infer the presence of a planet. And so there's actually two ways we can do that. So the first way is to actually measure the motion of the star. So as the planet orbits the star, it's actually going to tug the star back and forth by a very tiny amount. But if we measure the spectrum of the light emitted by the star, we can actually see a little Doppler shift, so a little red shift and blue shift of the light as the star is pulled towards us and then away from us by the planet. And so just to remind you, that's the same idea as if you have an ambulance driving past, the pitch of the siren gets higher as it approaches and then goes lower as it drives past you. So same idea, we're just doing it with light. So that change in the wavelength of the light from the star tells us that there's something in orbit around it. The amount that the star moves tells us something about the mass of the orbiting object, so we can tell the difference between binary star systems and stars with little small planets around them. And there's a periodicity to that motion, and that tells us the period of the orbiting object. So we know there's a planet there, we know its mass, and we know its orbital period. And so this is how the very first planets were detected around nearby stars. Although that's a great solution to the problem of how do you see really faint planets next to bright stars, this is actually not the most successful technique for finding planets. That honor actually goes to the second technique. So this is yet another clever workaround. So in this case, we're relying on the fact that a small fraction of the planets around nearby stars are actually going to line up so that once every orbit, the planet actually passes in front of the star. So there's an eclipse, much like the transit of Venus, some of you may remember from a couple of years ago. So when the planet passes in front of the star, it's going to block part of the star's light. Now, what we saw with the transit of Venus was something like the image at the top, where you see the disk of the star and you see the black dot moving across it. We can't actually see that for nearby stars, so all we see is a point of light that is that distant star. But what we can do is we can measure the brightness of that point of light as a function of time. So we're looking for stars that periodically dim in brightness when the planet passes in front of them. And from the amount that the star dims, we can actually measure the size of the planet relative to the star. So that tells us that there's a planet there. It tells us the size of the planet, and we can actually combine these two techniques together. The Doppler shift of the star, which tells us the planet's mass, and the depth of the eclipse when the planet goes in front of the star, which tells us its radius. And so mass and radius together tell us density. So not only have we now discovered a planet around this star, we now know something about what kind of planet we've discovered. So I can tell you if it's a gas giant planet like Jupiter that's primarily hydrogen and helium, or if it's a small, compact, rocky planet more similar to the Earth. So the most successful planet hunting mission to date is the Kepler telescope. Some of you may have seen it mentioned in the news. So The vast majority of these 5,000 planets and planet candidates come from the Kepler mission. So Kepler launched in 2009, and its mission was to stare at a single patch of sky, about 100 square degrees, located near the constellation Cygnus. So that's this little set of boxes right here. So this is where Kepler was looking. And what it was doing is it was measuring the brightness of about 150,000 stars in that patch of sky. And it was doing that continuously for a period of 4 years. So the goal of the Kepler mission was to tally up a list of all of the stars in that field that periodically dimmed in brightness. And then from that list to sift out this subset of systems which actually are eclipsing planetary systems. So it was amazingly successful. So as I mentioned, it found thousands of planets. It was also a really important milestone because it was the first survey that was really sensitive to planets as small as the Earth. So even though we discovered the first planets nearly 20 years ago, those planets were gas giant planets, more like the size of Jupiter. So the Kepler mission was really the first survey where we were able to find planets all the way down to the size of the Earth. And it turns out that there are tons of planets out there. So one of the things that we learned from Kepler is that most stars, like the sun, have one or more planets in orbit around them. So Kepler told us that planets are common. The other really interesting thing that Kepler told us is that small planets are more common than big ones. So if we count up the number of Jupiters around these nearby stars, and we count up the number of Earths, or at least Earth-sized planets, not necessarily in the same orbit, Kepler tells us that there are many more Earth-sized planets for every Jupiter-sized planet that we see. So that's encouraging. That tells us that, going back to that image of the night sky, most of those stars have planets. Many of them are small. So if we want to ask, what's the probability that there's another planet out there like the Earth, the odds are looking pretty good. But what do we actually do with that information? So one other important thing to mention here is that although Kepler was an amazing planet hunting machine, it was limited in one very important respect, which is that it was most sensitive to planets that orbit extremely close to their host stars. And that's just because of the geometry of the eclipses. So if you imagine you have your star and you need to see your planet pass in front of the star, the orbits of the planets are randomly oriented with respect to the Earth. So if you have a planet that's really close in, it can be tilted up or down by a greater amount, and you'll still see the eclipse. But as you imagine moving that planet further and further away, the range of angles where you see the eclipse gets smaller. So another way to put that is the probability that we'll see a planet eclipsing is inversely proportional to the distance between the planet and the star. So if the planet's really close to the star, our chances are pretty good. But as it gets further away, that probability goes down. And because Kepler was only looking at 150,000 stars, eventually that probability gets small enough that we just don't find very many of those kinds of planets. So Kepler found a lot of planets, but most of the planets that it found orbit inside the orbit of Mercury in our own solar system. So perhaps the most exciting thing to come from Kepler, at least from a science perspective, wasn't necessarily the discovery that there are lots of planets, but rather the discovery that most planetary systems look very different than the solar system. And so in order to illustrate that, I can show you just a scale drawing. So here on the top is a scale drawing of the inner region of the solar system. So this is about the region that Kepler was sensitive to. It could detect planets about as far out as Earth, but not much further. And so in this drawing, the distances are to scale, and the radii of the planet are to scale, not to the same scale. I've made the planets bigger so you can actually see them. But that'll give you an idea of the relative sizes and distances of the planets. So there's the solar system. That was what we had in mind before the survey started. Now I'm going to show you an example of a typical planetary system discovered by Kepler. So here's one of those planetary systems. It's really strange by solar system standards. So Kepler found that many of these stars have planets which are, even though they're very close to the star, are still much larger than the terrestrial planets of the solar system. So this particular example has 6 planets, all of which eclipse their star. And so the sizes of those planets, they're smaller than Neptune, but they're all a fair bit bigger than the Earth. And so we actually can, when we measure the masses of these planets, it turns out that they're relatively low density, so they're puffy. And that means that these aren't just like really, really big rocky planets like the Earth. These are actually more akin to kind of miniature Neptunes, little puffballs with a hydrogen-helium atmosphere on top. So that's a really strange kind of planet. There actually is no planet like that in the solar system, and that's a strange place to find them as well. That region of the solar system is very empty. There's yet another kind of planetary system, which actually we knew about even before Kepler. This was the very first kind of planetary system discovered around nearby stars. So that planetary system is a single planet the size of Jupiter, orbiting with an orbital period of just a couple of days around the star. So we call these planets hot Jupiters. They're extremely hot, and they're also quite large compared to all the other planets on this plot. So it was a big surprise to discover that most stars have planets that look more like the middle and the lower line, and that systems like the solar system are actually relatively uncommon. So less than 50% of all stars seem to have a relatively empty inner region like the solar system. So most stars look more like the middle and the bottom. So the question that I want to ask tonight is, why were we surprised by that? So what was it about our picture of how planets form and how the systems evolve that led us to think that this top thing should be the typical outcome? And so what was it that was unexpected about the bottom? So what do we need to change about our theory for planet formation in order to make sense of these new kinds of systems that we're discovering? So there's two possible answers. But before I go into that, let me just take a step back and ask, what was our story for the solar system? So before we even started searching for these planets, what was the story that we told that explained the sort of layout that we have in the solar system? So that story is something called the core accretion model. So the idea is that you build planets by gathering up all the material which is solid in your local part of the disk. So this is a disk of gas and dust orbiting around the young sun. So the dust is sticking together and growing and accreting to make these, if you're in the inner disk, it's going to be mostly rock cores. As you move further out, there's ice as well, so it could be a mixture of rock and ice. So you grow these solid cores, and eventually they get big enough that they start to grab onto some of the gas as well. So now you start to get a little bit of a hydrogen-helium atmosphere. And if you can grow long enough and big enough, eventually that atmosphere starts to collapse down onto the planet, and you grab even more gas, and then you rapidly blow up in size to become a gas giant planet like Jupiter. So with that picture in mind, the story that we told for the solar system, which looks like this, was the following. We said in the inner solar system, the cores that you build stay small. They aren't really able to grab onto much gas, and so that explains why the inner planets are mostly rock and pretty small compared to Jupiter and Saturn. Then we said, but in the outer region of the solar system, things are different. The cores grow bigger, they grow faster, they start grabbing gas early on, and so they are able to go through this whole process and acquire these giant, thick gas hydrogen-helium envelopes. So in the outer region of the solar system, you have bigger cores that grow faster and grab a lot of gas. So based on this picture, we would predict that when we look around other stars, the planets that we see close in should be smaller and mostly rocky, and then the more distant planets should be the ones that are gas giant planets with hydrogen and helium. So that was why it was so surprising, because what we found was basically this kind of flipped. Instead of Jupiter being all the way in the outer region of these systems, we see Jupiter is right next to the sun, or to the star rather. So what was wrong with our picture? So what are we missing here that that didn't allow us to anticipate that Jupiters could be close? So there's two possible explanations. So one is that our story of how planets form was wrong. Maybe not entirely wrong, but that maybe it's not so crazy to think you could make a gas giant planet right next to this star. It's just a matter of having enough stuff, right? If you just make your disk bigger and bigger, eventually you're going to have enough stuff in the inner disk that you could make as big of a planet as you wanted. So maybe we were wrong about disks, about how much raw material there was to begin with. The other possibility is that we were wrong about what happens after you make the planets. So In this picture that I've described to you, everything is very static. The planet sits at its particular orbit, and it just grows and grows and grows. But we know even within the solar system that the planets didn't stay put. There's good evidence that our gas giant planets actually have moved around a bit. So maybe the missing part of the story is actually migration, that something happened after the gas disk went away in these systems, which caused things to get shuffled around. You started out with a Jupiter, and then maybe that Jupiter migrated all the way in to a spot next to the star. So that's the question, is this mostly a story about planet formation and how to get that right, or is this mostly a story about how planets get rearranged after the fact? And this is a really important question for the search for life, because if you have a planet like a hot Jupiter that starts way out where Jupiter is in our solar system and comes barreling through the inner solar system, that's going to be really bad for any little planets that happen to be in the way. So there are important consequences, not just for the big planets, but for little planets that are sort of swept up along with them. So this question of why you get one outcome and not the other is all wrapped up in the question of how common or uncommon are planets like the Earth, and by extension, maybe potentially habitable planets. Okay, so let's go ahead and do some detective work. So let's try and think of ways that we could actually test these two theories. So can we figure out whether or not these big planets formed where we see them today, close to the star? So one important clue to where they formed is the material that they're made of. So I mentioned that planets grow initially by accreting the material that's solid in their part of the disk. Now we know that gas disks are hotter in the region close to the star, and that as you move further away from the star, the gas becomes cooler and more things start to condense out. So in the outer regions of these disks, you would have things like water ice that wouldn't be present in the inner disk. So if these close-in planets actually formed beyond the ice line, you would expect them to form with relatively water-rich compositions, because they're going to be able to accrete all that water ice. If, on the other hand, they formed close in, the planets should be relatively dry. So they should be balls of rock, maybe with some gas on top, but they shouldn't have very much water, because water is going to be mixed in with all the other gases in the disk. So if we could measure the bulk water content of these planets, we might be able to tell whether or not they came in from the outer disk or formed in close to the star where things were very hot. So how could we actually do that? I mentioned early on that we can measure both the masses and the radii of these planets, and that those two things together tell us something about their composition. So this is now just taking that and putting it in an actual plot. So here is the mass of the planet in Earth masses. So Earth is right here on the left, and then here's the radius in units of Earth radii. So this is Earth and Venus, this is Uranus and Neptune, this is Saturn, and that's Jupiter, just to orient you. So the red stars are the solar system planets. The black points are all of the extrasolar planets for which we have both of these measurements. So I mentioned that we have thousands of planets that we know of around nearby stars. There are only a few hundred of them that we can put on this plot, so this is now a much smaller number. So you can see that there are a lot of planets which are very much similar to Jupiter and Saturn. So these are the gas giant planets. Most of these are hot Jupiters. Remember, we're best at finding planets that are really close to their star. And so that's actually why these planets are a little bit larger than Jupiter. They're a bit hotter, so that makes them kind of a bit puffier. So just to translate that mass and radius into a composition, we can make theoretical curves, just sort of toy models for planets that have different compositions. So this light blue line on the top is a toy model for a planet that's just hydrogen. So this is the puffiest planet we could imagine building. And that line is a pretty good match for Jupiter and Saturn. So Jupiter and Saturn are mostly hydrogen and helium, and everything else is kind of just a little addition to that. As we go down into the left, though, you'll notice that Uranus and Neptune sit below this line. And that's because Uranus and Neptune have relatively large rock ice cores with a thick hydrogen-helium envelope on top. So they're kind of a mixture of two things. Even further down, you see planets that intersect with this blue line here, which is the line for a toy planet model that was made entirely of water. So it's a little bit simplified. Probably planets are mixtures of things, so even a water planet still probably has a rocky core, but close enough. If a planet was mostly water, it should lie pretty close to this line. And you can see that there actually are planets which we detect that look like water worlds. So if we want to ask, could any of these planets have formed in the outer disk, these potential water worlds are maybe the most interesting ones to focus on. Coming back to the question of terrestrial planets, you'll notice that some planets fall close to this brown line here, which was the line for a planet that's purely rock. And then down here, sort of the extreme case would be a planet that's pure iron. So there are a number of planets which seem to be rocky, like the Earth. Those are mostly very close to their stars, so they're extremely hot. So these are not Earth-like planets, but they're Earth-like in the sense that they're small and rocky. Okay. So let's focus on these water worlds. So I said that these are potential water worlds. So you're looking at this plot and you're thinking, well, there's the water line, there's the planets, what else could they be? So there's a catch here, and that catch is that there are 3 different things we can use to make our planets: hydrogen gas, water, and rock. But we've only measured 2 things. We've only measured a mass and a radius. We have 3 things we want to know and 2 things we've measured. And so that means that there's going to be a degeneracy between the amounts of those things that we need to match this measured mass and radius. And so just to illustrate that with a cartoon, here's just a simple water world where I have a small rocky core surrounded by a mantle, water-rich mantle. So that's a pretty good match for these planets. But I can also make an identical planet, at least identical appearing planet, which has a slightly larger rock core and then a little bit of hydrogen helium gas on top. So I can tune the amounts of those that I put in my planet to make it have exactly the same mass and radius as my water world. So what we're not sure about is we don't know if these are actually water worlds or if these are imposters that look like water worlds but are actually relatively dry planets, not much water at all there, that could have formed in place close to the star. And in order to distinguish between those 2, we need an additional piece of information. So the thing that we're missing is we're missing some information about the composition of the planet's atmosphere. If we could only measure that, these 2 would look very different. This planet would have a steam atmosphere, whereas this planet would have a very puffy, hydrogen-rich atmosphere. And so that actually is a pretty big difference if we could detect it. So amazingly, this is actually something that we can do. So these distant planets that eclipse nearby stars actually give us some leverage to say something about their atmospheres. And so the trick for doing that is going back to this eclipse. So remember, when the planet passes in front of the star, the amount of light the planet blocks tells us about the size of the planet relative to the star. But for planets that have an atmosphere, that atmosphere is going to be transparent at some wavelengths and opaque at others. So the amount of light that the planet blocks when it goes in front of the star is going to vary as a function of wavelength. And that wavelength-dependent eclipse depth is going to tell us first that the planet has an atmosphere, but also it's going to tell us about some of the molecules that are present in that planet's atmosphere. So this is just an example of an actual light curve that we measure. So this is the eclipse of one of these hot Jupiters passing in front of its host star. This measurement is made with the Hubble telescope. And so this actually is light curves going across the visible light spectrum. So here's blue wavelengths starting at about 300 nanometers on the bottom, going all the way to red wavelengths about 800 nanometers on the top. And so what we're trying to measure here is we're asking, does the apparent size of the planet vary? So does the depth of this eclipse vary depending on the wavelength that we look at? And you might notice that there's a different shape to the eclipse as we go to different wavelengths. That shape is actually due to a property of the star called limb darkening. So the edges of the star are a bit dimmer, and the middle of the star is a bit brighter. So that causes this curved shape, and that's a wavelength-dependent effect as well. So that's kind of a detail, but I just wanted to mention that it's not quite as simple as we might want it to be, that we actually have to know quite a bit about the stars that these planets orbit. So everything that I'm telling you about tonight, because everything is measured relative to the star, we only know the planets as well as we know the stars. So it turns out we have to do a lot of stellar astronomy in order to learn about the planets. Okay, just to tell you a little bit more about where the data actually come from. So I mentioned that that previous plot that I showed you was observation made with the Hubble Space Telescope. So most of our best observations of exoplanet atmospheres come from Hubble. But we also make some of our observations from ground-based telescopes like the Keck Observatory, which is on the summit of Mauna Kea in Hawaii. And so there are some pros and cons to observing with each of these telescopes. So the biggest pro to observing with the Hubble Space Telescope is you're above the Earth's atmosphere. So that makes everything really stable, nothing changes. We're measuring a time-varying signal, and so if you can do it from space, you get beautiful data. It's really the best possible data that you could want for this kind of measurement. The downside, of course, is that it's actually not very much fun. You can't go to the telescope for your observing run. Unfortunately, that would be awesome. So the way it actually works is I write a script that says, Hubble telescope, I want you to look at this star in this wavelength and to stare at it for this amount of time. So I write that script. I send it off to Space Telescope Science Institute, which is the organization that runs the Hubble telescope. They take my script, they put it in the queue. Maybe 6 months later, the telescope actually does the observation. And then I get an email in my inbox that says, your data were taken and are available for download. So it's beautiful data, but it's really not very exciting way to get data. So for that reason, I love observing at Keck and at Palomar, because there you actually have the opportunity to go to the summit of the mountain, go to the telescope, stay up all night, actually see the telescope point and look at the star that you want to observe. So it's a much more sort of hands-on experience. So going to Keck is great. I love going to Hawaii. It was a wonderful thing to do as a grad student, especially in the winter. I was a grad student in Boston. It gets very cold. So trips to Hawaii was definitely great. There's a catch, though, which is this picture is actually a picture I took as a grad student on the summit of Mauna Kea. I took this during an observing run in May. And you might notice, even though it's May, that there is white stuff in this picture. So even in the middle of the summer on Mauna Kea, there is snow on the summit. So when I went observing in Hawaii, I was not on the beach. I packed my winter parka, I packed my hat and my gloves, and I was on top of a very cold mountain observing these stars. Nonetheless, it was an amazing experience. Pluses and minuses, a lot of fun to do both, but it's really the Hubble telescope that's behind a lot of the most exciting discoveries about the atmospheres of these planets today. Keck actually has been great for other reasons, which I'll come back to in just a little bit. All right, so let's talk a little bit more about atmospheres. So I mentioned that Hubble is actually able to detect the atmospheres of some of these planets, but I didn't tell you which planets or what it was detecting or what we learned. So just to give you an example of one of the planets that I actually got to observe with Hubble, this is a Neptune-sized planet called GJ436b. So the names that we give to exoplanets, we name them after their host stars. So the host star is GJ436a. It is a star which is about half the mass of the sun, so that means it's smaller and cooler and dimmer than the sun. And this Neptune-sized planet goes around the star once every 2.5 days. So it's a very close orbit. But because the star is a bit dimmer than the sun, this planet, it's warm, but it's not, boiling hot the way some of these hot Jupiters are. So I would call it sort of an intermediate temperature planet. So we measure the mass and the radius of this planet, and that tells us that it has a bulk composition similar to that of Neptune, so it looks a lot like Neptune. We know that Neptune has a hydrogen-rich envelope surrounding its core, and so that's good for these observations because hydrogen-rich atmospheres are very puffy, and they create really strong absorption features when they pass in front of their stars. So hydrogen-rich atmospheres are the easiest kind to detect with the Hubble telescope by looking at these transits or eclipses. So we thought that this would be a really easy observation to make. We know the planet looks a lot like Neptune. It should have a lot of hydrogen in its atmosphere. It should be no problem to look at it with Hubble and actually detect the signature of its atmosphere. When we actually went and did that, we were in for a surprise. So it turned out that we saw nothing. For all we knew, this could have been a ball of rock. We saw no signature of any atmosphere whatsoever. we know it's not a ball of rock because we measured its density, and we know that it looks like Neptune. So the question is, what were we missing here? We had a great idea. We're going to measure the amount of light the planet blocks when it goes in front of its star, and we're going to do that at a bunch of different wavelengths, and that was going to tell us about the composition of its atmosphere. So what were we missing? It turns out that we neglected to consider the possibility that our planet might be cloudy. So when we look at the solar system planets, many of them have clouds. It's not crazy to think that planets would have clouds. But we kind of forgot that that same thing could be true for these extrasolar planets. So it turns out if you have a really high altitude cloud layer, that you can block the signature of absorption from the planet's atmosphere when it goes in front of the star. So usually when we observe from space, it's great. We don't have to worry about bad weather messing up our observations. But it turns out that for this particular measurement, we have to worry about clouds not just on the Earth, but also on other planets as well. So we ran into poor weather, which prevented us from detecting the planet's atmosphere. One fun thing to think about is the fact that this is a relatively hot planet. So this planet is about 800 Kelvin. The Earth is about 300 Kelvin, so it's quite a bit hotter than the Earth. And that means that the clouds that are present in this planet's atmosphere can't be water clouds like the water clouds on the Earth. So we think that they might actually be salt clouds, which is kind of a fun thing to think about. There are also even hotter planets that are cloudy, which might have liquid rock clouds or perhaps even iron clouds, if you want to get to even more exotic weather. Okay, so that's where we're at with Hubble. So we're looking at mostly gas giant planets and trying to detect their atmospheres and discovering that many of them, as it turns out, are cloudy. So we haven't really made much progress towards answering the question we started with, which is, are these candidate water worlds, planets that are close in but look like they could be about the density we would expect for water-rich planets, are they actually water worlds, or are they imposters, balls of rock with gas on top that formed in the inner parts of these planetary systems? So Hubble's just not quite sensitive enough to let us answer that question. Fortunately, NASA is building a successor to Hubble and also to Spitzer, which is the complementary infrared telescope. And so that newer, better, bigger Hubble is called the James Webb Space Telescope. It's scheduled to launch in early 2019. So we're all very excited to use it for these observations. And it's a much bigger mirror, so it's going to collect more light, which means it's going to make more precise measurements. It can also observe at a very broad range of wavelengths over the infrared, so it's going to be good at detecting all kinds of different molecules we might want to look for in the atmospheres of these planets. So it's going to be a big step forward. And I think this telescope is going to be the one that actually tells us whether or not these planets really did form close in, or whether or not they're water-rich imposters from the outer parts of these systems. Okay, so James Webb will do amazing things for bigger planets, but many of you are probably wondering whether or not it's actually going to allow us to study the atmospheres of Earth-like planets. So that would be an even more amazing thing to do. So Earth-sized planets are really hard. They're a factor of 100 smaller than Jupiter, so all of the signals we're trying to measure when the planet passes in front of its star are now 100 times smaller or more. So it's just a really hard measurement to make, even with James Webb. And so one way around that is, remember, we measure everything relative to the star. So when we shrink our planet down, our signal gets smaller. But if we could just shrink our star down along with the planet, maybe we could kind of make up for some of that lost ground. So the best planets, small planets, to study with the James Webb Space Telescope are small planets orbiting small stars. And so the best example of that is actually a system called TRAPPIST-1, which was discovered just a couple of years ago. And it's kind of a fun system. So the host star is about 10% the mass of the sun. So just when you plot it next to Jupiter, it's actually just a little bit bigger in size than Jupiter. And it has 7 Earth-sized planets, all orbiting around the star, all of which pass in front of the star as seen from the Earth. So there are 7 eclipsing planets around this star. Interestingly, they're at about the same distance from the star that the moons of Jupiter are from it. So you could think of this as kind of a stellar analog of the Jovian moons. But sort of practically speaking, a couple of these planets are at about the right distance from this very dim star. to potentially have liquid water on the surface, which we think might be important in the search for life. And because they orbit such a small star, we actually might be able to detect their atmospheres with the James Webb Space Telescope. Okay, so we have made a valiant attempt to detect the atmospheres and measure the bulk water content of these planets in an attempt to answer the question of whether or not they could have formed in place. Our best efforts were not quite good enough, so we could just sit back and wait for the James Webb Space Telescope to launch and get our answer then. But that's not very much fun. So in the couple of years while we're waiting for James Webb to launch, we thought we might try a different approach. And so this approach is to think instead about the reverse scenario. So instead of thinking about things forming in place, let's think about whether or not they could have migrated in from the outer part of the solar system. So there are a couple different ways that they might have migrated, but one sort of plausible story is you make a planet like Jupiter in the outer region of this system, but then even further out, you have another massive body. It might be another giant planet, it might even be a small star, and that small star tugs on your Jupiter's orbit and makes it more elliptical or eccentric. And so that elliptical orbit causes your Jupiter to eventually pass close to your star. And once it gets close enough to the star and the planet are going to tidally interact, and that's going to start to circularize the planet's orbit. So over time, the star is going to take out that ellipticity, the eccentricity, and it's going to make the planet orbit on a more and more circular orbit, until eventually what you're left with is something which is your Jupiter, but now orbits much closer to the star. So this is one kind of story we could tell for how you might take a planet like Jupiter and bring it all the way in close to the star. So the nice thing about this story is that it gives us a testable prediction. In order for this to happen, there has to be a third body in the system, and it has to be something big. If I put an Earth out there, it's not going to do much to Jupiter. It's just too small. So whatever is hiding in these systems, if this is the story that explains where hot Jupiters come from, we have a prediction that we should see pretty big things if we look in the outer parts of these systems. And as I mentioned earlier, this also has consequences for inner planets. So this process of getting a very elliptical orbit and then gradually damping that down into a circular orbit is going to tend to eject any planets that were in the inner part of the system. So there's another prediction here, which is that planets that migrate this way should be lonely. There shouldn't be any other nearby planets because you should have ejected them all during this process of migration. So sure enough, when we look at hot Jupiters, we think that they're pretty difficult to form in place close to the star. They're really big planets. It takes a lot of material to make a planet that big. And also when we look at those planets, we see that they very rarely have nearby smaller planetary companions. So hot Jupiters appear to be lonely. And that's an important clue that maybe they migrated via this kind of three-body interaction. Okay, so hot Jupiters should have outer companions if this is how they migrated. Do we know of any hot Jupiters with outer companions? So it turns out that we actually don't know very much about the outer regions of most exoplanetary systems. So this is now a diagram of the solar system to scale, same kind of diagram I showed you before, except now I've zoomed out to show you the entire solar system in one slide. So now we have the terrestrial planets in the inner region of the solar system, and we have our 4 familiar gas giant planets in the outer region. So the Kepler telescope looked for a period of 4 years. So the Kepler telescope was able to find planets about as far out as the Earth, but not much further. So for all the planets discovered by Kepler, we kind of see this part of the planetary system, and we miss all of this out here. The radial velocity or Doppler surveys have been going for about 20 years, so they can go a little bit further out. So those surveys kind of get us about the orbit of Jupiter, but neither of these techniques is really able to tell us about these outer regions. So it would be very easy for hot Jupiters to have distant companions that we missed in our original surveys because we just weren't able to look that far out. So what we decided to do was to use the Keck telescopes to actually go back and search in these systems. So systems where there's a close-in hot Jupiter, to look for the presence of distant massive companions in the outer regions of these systems. And so we did that using 2 techniques. One was this Doppler technique that I mentioned. If you just look for long enough, you can eventually detect very distant orbiting objects. So in this case, we're looking for outer gas giant companions. And then we also used a different technique that I'll explain in a minute called high contrast imaging to look for hidden stellar companions in these systems. So this is something that kind of would be a bit different than our solar system, but astrophysically speaking, we know that almost half of sun-like stars are in multiple star systems. So it would not at all be strange for these hot Jupiters to have a second star nearby. Okay. So how do we look for hidden planets in these systems? So I mentioned that we're measuring the Doppler shift, so the motion of the star towards and away from us caused by the planet. In this case, there's a problem, which is that usually we've only been looking at these systems for a couple of years. So this is now time in years on the x-axis, and then radial velocity. So this is just another term for the motion of the star towards us and away from us. So if you had a distant orbiting planet, you would expect the star to move towards you and then away from you, and then towards you and away from you in this periodic motion. But if you've only been looking for part of the planet's orbit, what you actually see would look something more like these black points here. So that's enough to tell us that there is something out there. We know it's got to be relatively big because of the amplitude of this motion, but we don't know exactly how big it is, and we don't know exactly how far out it is because we haven't seen a complete orbit. But we can still at least have the existence proof to say that there is something there. And so what we did was to look in all of our hot Jupiter systems and just count out the fraction of hot Jupiters that have one of these outer companions. And it turns out that it's quite a few. So about half of all the hot Jupiters we looked at have outer companions. So it's not 100%, it's not zero, it's kind of in between, but it's still nonetheless promising if we want to tell the story about interactions between the Jupiter and an outer companion causing it to migrate. So half is a good number. But we haven't yet looked at the other part of our survey. So half of hot Jupiters have another gas giant companion. How many of them might have hidden stars lurking nearby? So in order to detect stars, we need a different technique. So you might think it would be really obvious if there were 2 stars or 1 star in these planetary systems, but it turns out that it's actually surprisingly easy to miss that. And the reason for that has to do with something that astronomers call seeing, but is really just kind of how blurry or sharp is your image. So here on the left is an image taken with a small telescope of a random part of the night sky. And so you can see that each of these blurry blobs is a star. So there's star here, star there. And so the small telescope sees stars as larger blobs. Also, when you look through the Earth's atmosphere is constantly shifting and changing. And so that shifting, changing atmosphere also blurs the stars additionally by a little bit more. And you actually notice that effect. If you go out and look at the night sky, you might notice that stars twinkle. So it's that twinkling of the stars that causes them to be blurry in our images. So we can solve that 2 ways. One is we can go to a bigger telescope. The bigger your telescope is, the sharper the images that you can make. The other thing is that we can actually measure and correct for the blurring effect of the Earth's atmosphere. And so we do that using something called adaptive optics. So combining those 2 together, here this image on the right is the same part of the sky, but now taken on a bigger telescope with these adaptive optics. So here you can see these 4 stars here, and you might notice here this looked like a single star, but now we see that in fact it's 2 points of light very close to each other. So if you had one of these points of light was your hot Jupiter host star, it would be pretty easy to have a smaller, dimmer star nearby that you would miss unless you took one of these very sharp images. So we went and did exactly that. We went with the Keck telescopes and looked at all of our hot Jupiters, searched for hidden stellar companions, and this is what we found. So this is now just reversed images. So the star is the dark point in the middle. So all of these have hot Jupiters in orbit around them. And then you might notice that in every one of these images, there's a nearby fainter point of light. Here, here, here there's actually 2 points of light. So these fainter points of light are all stellar companions. So these are all multiple star systems. And this is actually a triple star system where the hot Jupiter orbits the sun-like star in the middle. And these are 2 very faint, dim, cool stars that are all part of the same system. So if you tally up the fraction of hot Jupiters that are in these multiple star systems, it again turns out to be about 50%. So half of all hot Jupiters are in multiple star systems. Half of them have planetary companions. And so that's good because that's telling us that there are a lot of companions out there. So this made the dynamicists happy, the ones that came up with this theory for how they could migrate. It seems like that actually works pretty well. Okay, one other fun thing to think about. So these systems that I was mentioning are systems where you have two stars that are relatively far apart, like hundreds of AU, so beyond the distance of Neptune in our own solar system, and the planets in orbit around one of them. We actually see also planets in a different configuration. So the Kepler telescope found about a dozen systems where you have two stars very close together, and then you have a planet in orbit around both of those stars. So those are systems that would be kind of like Tatooine from the Star Wars movies. So one really fun thing is that we're actually starting to find planetary systems which are like the systems from science fiction movies. And that system, one of the very first ones was Kepler-16. Okay. So hopefully I've convinced you tonight that we are finding many, many planets around nearby stars, that those planets are common, but also that the kinds of planetary systems that we're finding are very strange by the standards of the solar system. So most planetary systems have a configuration which is very different than the one we have in the solar system. And we're still trying to understand the reasons for that. So it might be that the disks, the raw material that's available to form planets, is more varied than we thought. But it might also be a story about how things get rearranged after the fact. So maybe you have these systems that start out with Jupiter's more distant, and then through some interaction with something else in the system, end up getting kicked into the inner region and maybe ejecting some terrestrial planets along the way. So we think that there are clues that migration might be a really important part of this story. We're also finding that there are many planets in multiple star systems, and this is a very new thing to think about. It's very different than our picture of the solar system, where you have one star and you have a disk around that star, but it's a very common thing astrophysically, and so it's interesting to think about the consequences of that for the kinds of planetary systems that you might produce. Also, although we're very good at finding planets around nearby stars, we're mostly finding planets in this region. So one very important piece of the picture that's missing right now is this region out here, which contains the gas giant planets of the solar system. And so this is something that we're hoping to sort of fill in coming years, both by pushing outwards with techniques like transit and Doppler, but also by pushing inwards with this very high contrast imaging technique that we're using to detect stellar binaries. So both of those together will hopefully meet somewhere in the middle, and we can actually sort of complete our census of these planetary systems, which will help a lot in telling stories about how they formed and evolved. So the final thought that I wanted to leave you with tonight is actually not one about individual planets or even stories about where planetary systems come from, but rather just to actually take a step back and to place all the planetary systems that we've talked about within sort of space. So this is just an artist's impression of our galaxy, the Milky Way. And here's the sun, which is located part of the way out from the middle in one of the spiral arms. And so what I want to do is actually just draw a little shaded region around the portion of our galaxy where all of these exoplanetary systems are located. And that'll give you an idea of the region that we've explored so far. So if I draw that shaded region, there it is. All of the thousands of planets that I've mentioned tonight are all within this one little patch of this one little arm of our own galaxy. So although we've made tremendous progress in discovering all these systems, we've really only begun to explore one small part of one local galaxy. So it's kind of fun to think about all the millions and billions of planets that are out there waiting to be found. And with that, I'll take questions. Thank you.